So this slide can effectively serve as an outline for the entire course. We're sensing data from the real world using a sensor or transducer of some sort. We do some signal conditioning on that, run that through an analog to digital converter to a microcontroller or a microprocessor, and then in a mechatronic system we often act upon the world as well. So from that microcontroller or microprocessor, we output information on something like a DAC, a digital analog converter, do some potential signal conditioning on that, and use that to control an actuator or transducer to affect the world. And the thing that I want to point out in this slide is that all of these red lines here are signals. And a signal is associated with the transmission of information. So I'm always having some kind of information going over those red lines, and that might be a resistance signal, it might be a voltage signal, it might be a digital or a discrete signal, and so we want to provide some metrics and some parameters around signals so that we can talk about them more intelligently. Now, two of the signal attributes that we're going to talk about most commonly are going to be that signal's amplitude and frequency content. And the amplitude is effectively the size of the signal, the magnitude that I might have of my signal at different points. And that can vary over time, of course, but my magnitude is really what I'm concerned about there. And that's going to affect things like the range that I need to pick for sensor. It could affect, I might saturate my analog to digital converter, for example. I might use too many bits for a particular variable type. So these are the reasons why I really care about amplitude of a particular signal. So the signal frequency is how a signal changes in time. And that would certainly affect things like the bandwidth of the sensor that I need to choose, and we'll talk about that a little more separately. It might determine how fast I need to sample my signal in order to accurately represent that signal in the digital domain. So frequency can have a lot of impact on my choice of sensor or actuator or ADC or all of these different things as well. So a waveform describes the shape and form of a particular signal, and we can classify waveforms in a number of different ways. One that we've talked about is classifying a waveform as an analog waveform, a discrete waveform, or a digital waveform. So an analog signal, of course, is continuous in time and amplitude, and that signal might look like that y-axis might be some y of t there. And my discrete signal, remember I'm sampling my signal now, but it can take still any value that I might have there. This might look something like y of n, where I have n samples, but those samples can take any value. And a great way to think about discrete signals is in the limit as my delta t, or my sampling interval, goes to 0, y of n is going to equal y of t, the continuous function that I have. And then for a digital signal, I also have a sampled signal over time, but in this case I also have quantized amplitudes. So my signal can only be at a specific number of amplitudes. So if I think of the signals that I might encounter if I'm talking on a modern smartphone, I would certainly have an analog signal that I'm speaking. My speech would be an analog signal. And at the microphone down here, that signal would also be analog, right? That's what is being received over the microphone and coming out of the microphone. So inside the phone, I would have a sample and hold circuit that's actually sampling that signal coming from the microphone, that analog signal coming out of the microphone. I'd be sampling that, and that would result in a discrete signal. And then finally, I'd have that sampled signal go into an analog to digital converter, and often the sampling circuit is part of that ADC, and the output of that ADC would be a digital signal. So I'd have the full spectrum of analog, discrete, and digital in this smartphone example. And the simplest type of waveform that you're going to encounter is a static waveform. And a static waveform, these waveforms do not change, or change slowly enough that it just doesn't matter for your application. And a static waveform would just look like a straight horizontal line. So I have y of t. I could also have samples here. I've just drawn the analog signal. That waveform has an amplitude, a naught in this case, and I would write my y of t equals a naught.